can we basically the question is, can we always be sure that recovery of rich functions or approximating rich functions is an easy task, as we have this morning seen the structure of them suggests. And maybe also one thing I say before I start with my slides is that especially for the people who come from statistics, where rich functions in the form of single index models or projection Pursuit regression is rather, I would say, classical topic studied since the 80s. But from my point of view, the most and crucial difference is that I talk about approximation in the uniform norm and not in the L2 norm. And from the results I've seen so far, I think this is really an important point here. So you should always keep that in mind. Whatever results I show you here, this is always about approximation in the uniform norm, and you cannot just transfer that to the L2 norm. So, okay, so maybe what is the basic setup or the background where I'm coming from? So my starting point is now not I say a real-world example or a real-world problem that I want to solve, but so I'm doing complexity theory, so I'm interested in generally how hard certain classes of problems are. And so my reference problem, which is my starting point, is the L-infinity recovery problem, or in general the recovery of functions in the uniform norm. And so what that means is I have some sort of, given a sequence of samples of an unknown function, which is defined on a high-dimensional domain. So D can be large, very large, arbitrarily large if you want. And I've basically only two information given, namely one, this is the sampling points that my algorithm might choose or be given, that I do not distinguish at this point. They can be chosen randomly or adaptively, that's all included. And the goal is to compute an approximation to the unknown function from the given data in the uniform norm. So I want to be that the pointwise error is small uniformly in all points of my domain. And so to make the setting even more precise is, so I said I have two sorts of information. The one sort of information is the data I can acquire practically, but I also have another source of information, and this is a priori information about my function, so that it has certain sort of regularity or that it has some structure, for example, that it is a rich function. And so what I want to understand now is, given that I use this a priori knowledge, how hard is my problem actually? That means, what is the worst case error that my algorithm, that the best possible algorithm will do for this with the given a priori knowledge? So, and this is very important to note, this is a worst case error, so that does not necessarily describe what you might observe in a particular example in practice when you have one given function, because this function can be well behaved. But what I ask here is, what is the worst possible thing that can happen given your a priori knowledge? For example, the a priori knowledge that I say my function is 2 times differentiable. What is the worst possible 2 times differentiable function that is out there in the world? And what will happen then? And so if you come from classical approximation theory or numerical analysis, then you're probably used to thinking in worst case errors or in errors. And and you ask yourself, how fast does my error decay in terms of the number of information I have, or the amount of information. And in information-based complexity, people prefer to speak about the information complexity, which is just the numerical inverse of the error. So instead of saying, I've given a number of samples, what is the best, or the best error I can achieve in the worst case, it's just the question turned around. I specify an error bound, or a tolerable error, and ask what is the minimal number of samples or information that any possible algorithm has to use to guarantee this. And yeah, so there's one, I would say this is one of the most fundamental results in this direction, namely that, so let's consider as domain either the Euclidean ball, so just the ball in high dimensions, or the cube in high dimensions. And let's assume that we know something about the regularity of so we consider functions defined on these domains, and we assume that we have certain form of generalized Lipschitz regularity, which means we're given a parameter k, which gives us the number of derivatives that exist, and or the order up to which derivatives exist, and such a parameter beta, which controls of the highest order derivatives their Hölder regularity. And yeah, the reason why I consider this now is because this sort of notion of smoothness fits very nicely to rich functions, and but you can basically also just think of CK functions, right? So this part here is not so important. But what is very important to note is so in high dimensional problems, it's not enough just to talk about a certain form of regularity in the sense that a certain number of derivatives exists. It actually plays a very, very important role how I penalize these derivatives. So how do I control how large these derivatives can get? And in this sense, I also take a very, very bad norm here, which you could say it's a problem oblivious norm, which makes minimal assumptions about the underlying function that could be there. Namely here, with this norm, where I just put maxima everywhere, that basically means that every derivative that this function has can be large simultaneously. So it can really, in every direction of my space, every direction of derivative can be large at the same time. Okay, so because this norm point becomes important next, because so there's a classical result. I mean, this kind of object is a standard object of approximation theory, and there are very classical results that show you that this rate of convergence that you get deteriorates quickly with the dimension, right? So if I want to have the same, say you fix some r, and say I have in the univariate case my function square decay like n to the minus r. I mean, you basically have to scale the smoothness linearly with the dimension to get the same decay rate. And people often talk about this as the curse of dimensionality, but this has nothing to do with the curse of dimensionality. Because the problem is what's happening underneath is, I mean, first you have additional dependencies on the dimension and the constants that are traditionally not studied. So where you actually do not really know what is happening here that could kind of mitigate the bad asymptotic decay. But more importantly, actually this asymptotic decay kicks in only very late. So even if we would improve that would not necessarily tell us anything about what would happen for small n. So and that's why it's like a fundamental result of information-based complexity by Novak and Wozniakowski, which really showed that when you consider this norm, then it's really the case that no matter whenever you want to achieve a non-trivial error, which is in this case an error smaller than 1, given how we set up the problem, then you have to use exponentially many pieces of information, no matter what algorithm you use. It's inherent in the problem. And so the question is then, if that is the case, I mean, you might say now, okay, then function approximation is a hopeless undertaking. I mean, what should we do? But of course, the question is, yeah, okay, is the setup here really realistic? And there's a number of points how you can play around with that. And one thing I'm going to do now is to study what happens when I assume I have a rich function. But I want to know, this is not the only thing you can do. It can already have quite some impressive effects if you just play around with this norm. So you do not really change the classical notion of smoothness. You just play around what norm you have here. But I stick with this kind of norm now, so this very bad norm, and wonder what can happen. So, and maybe I'll also write down what we can hope for. So people who are interested in complexity theory. So this is an example for an intractable problem. It's worse, it suffers from the curse of dimensionality because really the information scales exponentially in the dimension. But generally, so any problem where the information complexity is exponential in 1 over the error, or the dimension is called intractable. And so that's the bad thing. And say the good things are, I mean, yeah, the classical thing where I guess we all would agree on, if I can bound this information complexity from above by something, yeah, which is polynomial in D and in 1 over epsilon, then this problem is said to be polynomially tractable. Yeah, that is, I guess, where everybody would agree. This is what you have in statistics, numerical analysis. Everybody says, yeah, this is a good, well-behaved problem. But the fact is actually that as long as I stick to function classes where every variable can have the same importance, so where I only play around with smoothness, I can never reach that. They are all polynomial intractable. So that is why people, yeah, started to introduce weaker forms of tractability. And so the best thing that you could achieve with such classical smoothness spaces is quasi-polynomial tractability. And this is if your function behaves only mildly worse than a polynomial in epsilon d. You have to think a while about why this is the case, but this is not too much worse than this. And then there is weak tractability, and yeah, this basically says there should be no exponential dependence on 1 over epsilon or d, but this is not stated with such a nice formula, but in a more abstract way, where you say that the logarithm of the information complexity should go faster to 0 than 1 over epsilon plus d when I let this go to infinity. Yeah, this is called weak tractability. Okay, so okay, I introduced these notions now with a mathematical explanation or motivation, namely classical smoothness spaces cannot be polynomial tractable. But yeah, why should they be interesting from a practical point of view? I mean, if you think about the classical example from data analysis or statistics, where you say what you're interested in is actually something like a clinical study where you have to examine patients, then I would say everything that shows not much more than a linear scaling behavior in D should be considered practically intractable. But on the other side, if you think about problems from numerical simulation, so where it's not really about gathering data in real life, but more about computing something on your computer, and the data you have is actually data you also simulate on your machine, Then Moore's law, which guaranteed now for like 70 years that computational powers scale exponentially, then it makes also sense to talk about these weaker forms of tractability, because when I can show for a problem that it is neither exponential in 1 over epsilon or in d, this at least means that if I just wait long enough until computers become fast enough, then, and storage capacities become big enough, then I can all of a sudden solve my problem. And to be honest, I think what we see now with deep learning attributes to a large extent to this. So it's not that there are really new ideas out there. The ideas are all 30, 40 years old, but computers became fast enough. So this is why these kinds of, which, in the first place, they do not make sense, seem to make sense, but as long as computers become exponentially faster, everything that has a sub-exponential dependence makes sense. It makes sense to call this then a tractable problem, because time will solve the problem for you. Okay, so this is just to give you an idea of the background where I'm coming from. So now I want to investigate these kinds of functions for rich functions. So what kind of tractability can I get when I assume in this problem set up here that I have a rich function? So, and maybe to wrap up quickly, so we all have seen now what a rich function is, so a couple of times, so I go quickly over this. But maybe let me discuss the algorithms we have seen this morning from my perspective. So, and there was first, I mean, it has been mentioned a couple of times, this approach by Cohen, Lipschitz, Devore, and Karicharian and Picard. And so what they did is basically, so they assumed they have a rich function, and then most importantly, they assumed to know a priori that the rich vector is positive, so that it's contained in the first orthant of your domain. And why was that helpful? Well, first of all, it meant that, so let's do, so this assumption here, this is a technical assumption basically. It means that I need this to pose my problem well, because if I say my profiles are defined on -1, 1, then if I say that my rich vector is less than 1 in the 1 norm, then I can bound the maximal value the inner product can take, and so I assume that my values stay within the range I have pre-specified. Moreover, when I do it like this, then I can actually rewrite my rich, so the rich profile and the rich vector are not uniquely defined, but actually, so whatever initial profile and rich vector I have, I can always rewrite it like this. So here, instead of the original rich vector, I put the L1 norm normalized vector. And the profile here is basically the rich function samples or in direction of the signs of my rich vector. And so these ingredients together, they are very important, because that is what makes this intuitive algorithm we've seen this morning work. Namely that I can, because now I know the signs of the rich vector a priori, I know that in which direction of space I have to look for a point where the derivative of my profile is large. And then this problem is really not, it's basically as difficult as a univariate problem, because I only have to spend d samples to approximate the gradient, and the rest I use normal spline theory, and this gives me an upper bound of this form. So here I already see, okay, when I make these assumptions, my problem is polynomial tractable. Everything is fine. And oh yeah, maybe another thing I should add, because this becomes important later. What has not been discussed so far is what do I do in case that I do not find such a point that the derivative is large? Well, then because I know that I have sampled the whole relevant part of the profile's domain, if I have not found such a point, yeah, well, then it means that the derivative is small everywhere, so I can approximate my ridge function just by a constant function, where I just take the maximally observed sample and the minimal observed sample and take the average of that, and that will work. So in overall, these two steps taken together, I end up with a polynomial algorithm. Okay, so that was approach one, which heavily relies on, first, that I am on a cube, and second, that I assume that my ridge vector has positive entries. The second line of research, which we have seen this morning, is that I assume I know from the beginning on where the profile has a large derivative. And, well, actually, I have to assume that it is large in the origin due to concentration of measure phenomena, but okay, that's too far now. But so let's say I have to assume that the derivative is large in 0. If that is the case, I do not have to search for a point of large deviation, but I can, yeah, it's all about what we've seen this morning, that you just, yeah, you approximate the gradient and, yeah, then normalize and again use just standard spline theory to approximate your profile. But here two things are a bit different now. So first of all, I have to, in this model now, I have to assume that the 2 norm of the ridge vector is less than 1. Again, to assure that when I take this inner product here, that this will stay within -1 and 1. And also, is now you have, again, the profile and the ridge vector are not uniquely defined, but it's a bit different now, the relation. So again, I can say, okay, instead of the original ridge vector, I put here the ridge vector normalized by the 2 norm. But interestingly, I also have to put the same vector here in this rescaled version of the profile. And that makes really a huge difference, right? So in the other case, we basically just, because here it was the signs of A, that was what allowed that if I tell you the signs, and I mean, this is nothing different, right? This just says every sign is positive. So if I tell you the signs, I basically know that from the beginning on. Here the situation is already much more strict, because here it is not enough that I tell you the signs, but I really have to tell you the ridge vector itself, or at least the L1 normalized version, L2 normalized version of that. So from this argument, you can already get this gives you a hint that the approach which worked in the other case cannot work here. Okay, so that's why we have to stick with this. But if we have this assumption, then same as before, standard spline theory gives us a polynomial bound. Okay, so, but the interesting question is now, what happens when I remove any of these additional assumptions I made about the ridge function? So, and let's start with the case that I remove this assumption that my profile has a large derivative in the origin. So then the class I consider now is basically the same as before, just that I remove this assumption. And okay, let's add we'll also consider this not only, yeah, we had before that we can use compressed sensing, that it helps us further, and if I assume that my ridge vector is compressible. So, and I also want to consider the question how much this compressibility still can help if I do not have this assumption. Okay, so, and yeah, maybe so I do this one time to give you an idea how this business works to prove that problems are really hard. Namely, you have to prove lower bounds for the information complexity or your minimal worst case error. So that means you assume you're given any algorithm, doesn't matter. Somebody throws an algorithm to you, and my job is now to find a bad input, as bad as possible. So in IBC, the word fooling function is commonly used. So I'm looking for functions that fool my algorithm. And how would that work here? So assume we're given an algorithm A, and now there are sampling points, x1 to xn are the sampling points that are used by the algorithm if the 0 function was the input. So if I put 0 to the algorithm, then this is the sequence of points. The sequence of points might be chosen adaptively, but on the input 0. And what I show now is that basically I can force I can find now non-zero functions that force the algorithm to think that he sees the 0 function. And how does that work? So first ingredient is I need a bad profile. And we already see this bad profile does not have the property that the derivative is large in this 0, but it's 0 here. And only for a very small range here at the end, I let this thing then grow as steeply as my smoothness assumptions allow. So in this case, when I set R to 1, then I can use a Lipschitz continuous function. So and this then grows just like with anyways, what that means is that that the infinity norm of this object here is just the size of this range here, so just tau. And the second ingredient is I need a fooling or a bad ridge vector. And there the idea is now, okay, so my sampling points, I don't know where they are, but I know they're somewhere in the Euclidean ball. And so what I try to, and I have a certain number of them, and I try to put, I put epsilon balls around them, and then choose my ridge vector from the sphere, from the L2 sphere, from an area which is not covered by these balls. And to formalize that, I'm looking for an A star such that for every of these sampling points, the inner product is less than 1 minus epsilon squared half. And the question is, of course, now, how large can I choose these balls? I mean, it's clear then when I make a very tiny epsilon around it, then I will certainly find something like this. But the question is, what is the largest possible epsilon? And so I mean, I guess everybody agrees then when I choose the ridge vector like this and this profile, then I make an uniform error of epsilon squared half. And if I now choose R bigger than 1, so allow more than Lipschitz regularity, then this is also easy to see. Then instead of epsilon squared, I have epsilon squared to the R. So the regularity just gets into the epsilon. And so the important question now, what is the smallest possible epsilon for any algorithm, right? So for every possible selection of points here. And it turns out that this is given by a well-known quantity from approximation theory, namely the entropy number of the sphere measured in L2. And the nice thing about this is now, this object is, at least its behavior in n, and so in the number of sampling points and in the dimension, is completely understood since 2001. So I actually do not have to work anymore. I just have shown now that this is the lower bound, and I can just take the known results for these things here, and this gives me a number of interesting insights. Namely, if I choose p equal to 2, so there is no compressibility whatsoever, then this problem suffers indeed from the curse of dimensionality, because the entropy numbers, they do not decay until n equals 2 to the d. And after that, I get this decay n to the minus r divided by d. So this is quite surprisingly, in this scenario here, not only that I have no error decay whatsoever pre-asymptotically, it's also that asymptotically I get this very, very bad rate you usually have for classical isotropic spaces. So it seems, you see here really that this assumption that I know a priori where my profile has a large derivative is absolutely essential. Otherwise, I completely change the complexity of the problem. And if I now allow compressibility, it gets a bit better. So because then the entropy numbers show a pre-asymptotic decay, but this decay is only logarithmic in n. Now maybe I write that. So now I have a lower bound from that shows that it's bounded from below like this. Yeah, well, and here basically so here you have something like the smoothness. No, sorry. This one. So it is a very slow asymptotic decay, but there is one. And okay, so far I just talked about the lower bound, but in fact you can get an almost matching upper bound when you just use plain, simple, piecewise Taylor polynomials. So I skipped that, but you basically can get matching upper bounds. So this really is the pre-asymptotic behavior of the worst case error, except for what's happening here. So that's not completely matching. But so you see, I mean, then compressibility still helps, but yeah, not really. I mean, logarithmic decay, that's quite slow. Yeah, maybe what I should also say is, yeah. So let's interpret this. So in terms of this language here, so we've seen that if p equals 2, then the problem suffers from the curse of dimensionality. Interestingly, when p is not equal to, it never suffers from the curse of dimensionality. It's just intractable as long as my smoothness is not large enough. So basically, if this thing here is too small, then the logarithmic decay is too slow to have a tractable problem. And once the regularity gets large enough, yeah, then you have a strong enough logarithmic decay to get this weak tractability thing. But this is, I mean, yeah, there I would agree that, yeah, I think in general this bound tells you a lot. Whether this is now weakly tractable or not is basically a question of how I exactly define this thing here. But yeah, so the important point to remember is this logarithmic decay in n. And that this decay gets moderated by the degree of compressibility. So, okay, so that was for the ball. I should also add that this positive result we get here, that there's at least some some slow decay, is actually attributed to the fact that the domain is so small. If I would really use a domain which has volume 1, so, and the Euclidean union ball does not have volume 1, but if I blow it up so that it has volume 1, then this positive weak tractability results would not be there like this. But still the curse of dimensionality would not be there. Okay, so let's try to get something similar for the cube, and this is a cooperation with Benjamin Dörr from École Polytechnique. And so we ask now what happens when, in this model of Cohen et al., if we drop the assumption that we know the signs of the ridge vector in advance. And yeah, so so the whole analysis there is much more complicated than for the cube, because we do not have we cannot reduce everything to entropy numbers anymore. But I can give you the basic ingredients. So to get a lower bound, yeah, so basically what I have to reach is, so I can still work with these profiles, but now, so here on the ball, the nice thing was that, so entropy numbers actually say something about Euclidean distances, but I need something about inner products. But when I'm in the Euclidean ball, then I can relate distances and inner products via Cauchy-Schwarz. And now, when my domain is the cube, I do not have this. Cauchy-Schwarz is too weak, so I cannot rely on this, on this relationship between distances and inner products. So I need a different mathematical tool to control inner products. And on the cube, an easy available tool or a standard tool, which actually turns out to give some valuable results here, is Hoeffding's inequality. So with Hoeffding's inequality, you can basically construct the following. So given a number of sampling points, where this number has to be smaller than epsilon to the m, say 2 to the m, then I can always, so then I have sampling points z1 to zn given. And now by Hoeffding's inequality, I always can make sure that as long n is smaller than e to the m divided by 8, that I will find a point from the L1 ball such that the norm is less than the 1 norm half. So, or otherwise said, that the 1 norm is exactly given by m to the minus 1 over p. And this now is my tool, because then I can control, I choose now profiles which are 0 as long as, until A1, 1 norm of A half, and after that I let it grow. And so this is the basic idea. And interestingly, I get a quite similar lower bound with that. So now again, R is greater than 0, and P can now be anything between 0 and 1. And then I get the following lower bound, that as long as n is between d and e to the d8, then the minimal worst case error is again bounded from below by this logarithmic term. And as you see here now, if I choose p equal 1, so there's no compressibility whatsoever, then I have again the curse of dimensionality, because there's no error decay for d between, until an exponential number of sampling points. And so you see this looks quite similar to this, and actually it's an open question whether there should be a logarithm or not. It's not clear. So because it's an artifact at this point from Hoeffding's inequality, which does not give this this thing. So one thing I can say very quickly is that because I used Hoeffding's inequality, this proof is rather easy to extend to the randomized setting, so where I allow my algorithms to use random sampling points. It's technically you have some details, so how much time do I have left? 20 minutes, oh, okay. So I can show math to you, so very good. Okay, so then let's discuss how this works. So we want to do the same thing in the randomized setting, because we know in many situations, so for example integration, their randomization is a very, very good thing. It improves the complexity of problems in some cases a lot, and we want to find out if this could also be the case here. And so the basic thing is now, before we had our key lemma, which was by Hoeffding's, just a corollary of Hoeffding's inequality. But because Hoeffding's inequality is a probabilistic tool, it's rather easy to combine then two sources of randomness. Because what I did with Hoeffding was first say, okay, I consider my fooling rich vector to be a random vector, and then control probabilities, which then say, okay, if the probability. So what I did before was that if I can control the probability that for random vector A, all these inner products are, say, less than 1/2. If this probability is larger than 0, then I know such a vector must exist. And that was for, in the deterministic setting, that was enough. I just needed the existence of such a vector. Now, I actually need a bit more, because what I need now is that my, oh sorry, this should be Z. So what I need now is that now my my sampling points are also random. So what I need now is a statement of the form that there is a rich vector such that this probability, that the inner product between this fixed rich vector and the random sampling points is less than the norm of this thing, 1/2. And the trick how to get this is actually, so I think in information-based complexity is most of the time called this method of Bach-Wahloff. What you do there is, so you have the randomness in your sampling points, and now I also take again the randomness in the rich vector, and it's relatively easy to control what the randomness does in both things. And or say, yeah, let's write it in just give the basic argument. So I have, let's say I want to control this thing in expectation. Then I would have, okay, a random A here and a random sampling point there. And so, and now this E here, say, is the randomness with respect to A and the randomness with respect to X. But the nice thing is now here I can change the order of taking expectations, and that's what I basically do underneath there. So I know that when my expectation is, when I first put that inside, then the randomness with respect to the sampling points is gone. So I can use then this Höfting's inequality then again to get an A, and yeah, well, then I have to control the error between, with respect to this A. And yeah, if somebody is interested in the details, you can look for the method of Bach-Wahloff. This is a standard trick, so nothing new. But yeah, this is the important key ingredient, that I can change the order of expectation. And when I do it like this, so that's that. So with respect to this A, it's a simple standard business. But now to really control what a randomized algorithm does, there's one ingredient more, namely, so my algorithm can not only randomly sample, he can only randomly guess a function by which he approximates the unknown function. And I also have to control this error. And so roughly sketched, how does this proof work now? So the ingredient I start with is, so this omega prime is the set of all bad rich vectors I can choose from. So right, that's what we had before. And then, so this is what I start with. This is my set of bad rich vectors. Then there is this phi 0. This is the random function the given algorithm as n would use if I, now again, present the 0 function as input to this guy. And here comes now the trick. So in general, it could be that this algorithm is just very good at guessing what my rich function looks like. So he does not, it could be that he does not need these sampling points. It's just maybe the structure of this rich function, I mean, it's basically a function that varies along one direction in space. So maybe there's a guessing scheme that allows me to, with one random guess, to get very close to this. And so to rule this out is we do the following. So this FA here is, this is just so G star is again this flat profile, which is 0 and then just grows. And I just look at these functions that I get when I vary over any of my possibly bad rich directions. And this random vector A0 is now if it should happen that the random algorithm guesses one of these rich functions right, then I take this vector here. This vector represents this A. So you get that? Right? So I just look overall. This is a finite set, so I can just look at every of the things and look if the randomly guessed function comes close to one of my bad fooling functions. And if for one of these A's it happens, then I just take this A. And now the nice thing, okay, assume it happens, so the algorithm did a good shot. Then I try to control now that there are still enough other A's such that this inner product between the signs of this vector and is again smaller than what we've seen before, this A1 norm half. Because it's clear that if I have this, I mean, then I'm basically again looking as one of these rich functions there, and with this I just make sure that whatever sampling points he will use then, they will all land in this area here, so that he will just see 0. And the kind of interesting thing is now that if you construct this vector this way, it is kind of just another random sampling point for us. So I now just take the random sampling points this Sn uses anyway, and take this vector, the signs of this vector here as the n plus first sampling point, and then I apply this Bach-Waloff trick. And with that, I indeed get almost the same lower bound as in the deterministic setting. So I basically just pay the price so I get a slightly larger constant, smaller constant, and here it's not 2 but 4 and n plus 1. But again, it is enough to say that from a complexity theoretical point of view, nothing has changed, right? I have just shifted slightly different constants. Especially, I have again the curse of dimensionality if I have no compressibility. Okay, so yeah, just said. So there's now one important thing. So when we talked about the ball, I quickly said, I just showed you how to get lower bounds, and then I said, getting the upper bound is easy, just do Taylor polynomials. It turns out it's very, very difficult to get matching lower bounds for these. So only in case where p equals 1, there it's easy I mean, there you're not really interested in an algorithm that gives you an upper bound, because you know the problem suffers from the curse of dimensionality anyway, but it's very difficult for p smaller than 1 to get an algorithm that reproduces this lower bound. So actually, for this class I consider here, so for the class of all rich functions such that the profile is Lipschitz continuous or generalized Lipschitz continuous, and the norms of p norm of A is smaller than 1, I do not have an algorithm that works on this. But still, of course, there's the idea, isn't it possible to generalize the algorithm developed by Cohen et al. To work also in the case that if I drop this assumption, and indeed it is possible, you can construct such a vector, but I need an additional assumption. So I have to restrict my function class and have to throw out rich vectors whose one norm can become too small. So if before the situation was that I allowed basically every rich vector from such an LP ball, right? I have to exclude now, I have to cut out a 1 ball out of this LP ball. We will see in a minute why, but what this basically means, though, before it's we spoke about compressible rich vectors, but compressibility, as we always think about compressibility, saying that, yeah, I can approximate, compressible vectors can be approximated well by sparse vectors. And that's true, but actually when I just take the LP ball as a model, there are also cases where just the norm of the vector is small, right? So, and then actually, yes, it's true that I can approximate that well by a sparse vector, but just the reason is then not that I found structure, but just that the whole vector had a very small norm. So any vector would approximate that well. And this actually causes a problem for the algorithm we will see in a minute. So here I really have to stipulate true approximate sparsity. So I really have to enforce that my rich vectors have S components substantially larger than the others. And if that is the case, then I can indeed generalize the algorithm by Cohen such that it reproduces this bound. So under additional assumption, I can reproduce this bound. And maybe, so what's what are the basic ingredients? What do I have to change? So the point is now, since I do not know the signs of A anymore, I don't know what is the direction in space where I have to search for a large derivative. But what I can do, or at least just try, is, okay, if I don't know it, let's say I just randomly guess one. So so the algorithm I use now, or one component, is just, instead of a fixed sign vector, I give now one sign vector to it. And I mean, I can do the whole business. If I sample along this direction in space, and I find a large derivative, then I'm fine. Then I don't care anymore than that I have not searched along the correct direction, but because I found something large. That is, so to say, the easy case. I can do everything as before. The complicated thing comes, what if I do not find a point of large deviation? Because now, so before I was in the situation that I really was sure that I had sampled everything, that I really had seen the whole profile. Now, when I do not search along the correct direction, but just the number of signs are correct, then there are parts of the profile that I never see. And so what actually becomes difficult now is, in the analysis, is to control this step here. This one here. That becomes hard now. Because before it was easy. I knew I had seen everything, so if I had not seen a point of large deviation or no large derivative, I knew my profile was basically constant. There's not much that could happen. How can I assure this now? And there the whole thing becomes tricky, because I have to control the number of signs I guess correctly, or guess or find correctly. And so I say we have, so there are D signs, and say we have S signs are matched correctly. So the S signs that correspond to the largest components of the rich vector, if I match these correctly, then I can, simplifying, do the following. I again take the constant as before. So I take the maximal and minimal function value I've observed over my whole run. And now then I split as follows. So first, so this F can be written like this. And then I introduce this GV where I made a good control or where I guessed the signs good, sufficiently good. And now so then I split my error into two parts. And on this part here, I'm back in the old business, because there I know, okay, this thing I've observed, I have not found a large derivative, so this part of the profile must be approximately constant. There I can do the same analysis as before. The important thing now is that I have to control how close this thing here is to the true profile. And there is where it becomes tricky now, or where it becomes important that I exclude certain rich vectors, or that I really need approximately S-sparse rich vectors. Because if you think of this, if I have my, if I have this profile GV here, I mean, this is basically like the true rich function along this direction V. So this is G inner product of the true AV times T. And of course, I can rewrite this now with respect to the true profile, namely by so I just normalize by the one norm. Then I have the one norm here, right? So, and then I see that actually the difference of this thing and the true profile is governed by this term here. But there I divide by the one norm, and that's why I need a lower bound on my one norm. That's why I have to exclude too small rich vectors. And well, but if I do all this, so then the overall algorithm looks like this. I randomly draw sign vectors, and for each of these things, I try to find a large derivative. If I succeed for one of these, then I'm back in the old business. Nothing has changed. I just do the same analysis as Cohen did. But if over all of these runs, 2 to the s runs, I do not find such a thing, then I approximate with the average of the minimal and maximal function value I have observed for all. And if I do this, this gives me this gives me in terms of the exponent here matching bounds. But again, I have to say this is for a different class, right? So I cannot really compare these two. And the two classes only coincide if P equals 1. Then they are the same. Yeah, so close with this. With the summary here that, so we see in both cases on the ball and on the cube, I can have the curse of dimensionality. I can have weak tractability if my smoothness is large enough compared to the compressibility of my rich vector. What I did not present is that, say you can, okay, I leave that, I have not explained that before, but so I can, at least on the ball, I can have quasi-polynomial tractability if I take infinite smoothness. That's possible, and yeah, well, polynomial tractability I get when I make on the ball, I only have this additional assumption, and on the cube I can choose between either this assumption or that, that I say all components have to be larger than 0. So in that, so to close, you see that although a rich function is a very simple object at first glance, if you really do a thorough complexity theory for this thing, there a lot of ugly things can happen. And what especially causes a lot of problems to, in general, understand what's happening is that the behavior of inner products depends on the form of your domain. And this is something, which in the beginning you don't think about this, but this can cause issues. So thank you.